Good day, everyone. Today we are going to discuss about laboratory glasswares. This is the second to the last topic that we are going to tackle for the first semester of this school year. And I hope you would learn a lot from this discussion because as you move on with your student life, especially as a medical technology student, you're going to get acquainted with this apparatus, glasswares, and even equipment when you proceed to the second, third, and fourth level of the course. So it's best that we start early for you to learn the different glasswares and equipment that medical technologists use inside the laboratory. Laboratory glasswares, or commonly known as labwares, are either made of glass or plastic. If they are made of glass, they are usually more expensive and they require more care in cleaning to prevent breakage and scratches. Today, most laboratory wares are designed to be disposable, especially those that are made of plastic. And the reason for that is to eliminate the possibility of contamination of solutions due to inadequate cleansing. And also, most plastic wares are not reusable. So after processing the specimen, you really have to discard the container immediately and not reuse them. Now let's go to the different types of glassware. So we have five types that are being used inside the laboratory. So we start first with the borosilicate glass. So for the borosilicate glass, we have two most common brands used. We have Pyrex and Kymax. So these type of glassware, it's the most commonly used glassware and it's used for heating and sterilization purposes. And most of the laboratory glasswares we have in Angelo King are made of borosilicate glass, and we are using the brand under Pyrex. So this kind of glassware is characterized by a high degree of thermal resistance, which means that if you're going to use the glassware for heating solutions or heating the agar, it would not easily get broken or break. Okay, the next we have the boron-free glassware or soft glass. This one is made for high resistance to alkaline solutions, and the thermal resistance for this type of glassware is less compared to borosilicate glass. So there is a possibility that it would break if you're going to subject this one to high temperatures. Third, we have Corex with the brand name of Corning. This is a special alumina silicate glass that has been strengthened chemically and thermally, and it's 6 times stronger than borosilicate glass. That means that if this is 6 times stronger than the borosilicate glass, then it's more expensive. Number four, we have the flint glass. This one is made up of soda lime glass and a mixture of calcium, silicon, and sodium oxides. However, this type of glassware, it has poor resistance to high temperature, and this one it's used to make disposable glasswares. And lastly, we have the Vicor. This type of glassware can be heated to 900 degrees and it's used for extremely high temperature. For solutions that need heating at a very high temperature, you can rely on this type of glassware for as container for the solution. There are also different types of plastic wares that are used inside the laboratory. So we have three. The first one is the polyolefins or the polyethylene or polypropylene. These are chemically inert resins. When we say chemically inert, that means that the substance is not generally reactive, or it's another term for inactive with respect to chemical reactions. Resins, on the other hand, these are viscous substances that are converted into rigid polymers through a curing process. So our polyolefins, they are generally resistant to acids, alkalis, and salt solutions. Next, we have the polycarbonate. This type of plasticware has a clear appearance, and because of its strength, it can be used for centrifuge tubes. However, it is less chemical resistant than polyolefins. And the third type of plasticware is the fluorocarbon resins or the Teflon. This one is also chemically inert and it's used for temperatures from negative 270 degrees Celsius to 255 degrees Celsius. So there is only a range of temperatures in which you can use this type of plasticware. It provides non-wettable surface and it's used for stir bars and tubing. Now let's take a look at the common glasswares used inside the laboratory. The first glassware is the most common glassware we can see or use inside the laboratory, which is the test tube. So our test tube is also known as culture tube or sample tube, a common piece of laboratory glassware consisting of a finger-like length of glass or clear plastic tubing, usually open at the top and closed at the bottom. Looking at the definition of our test tube, we can see two other names. We have culture tube or sample tube. Culture tube because in the microbiology section, we often use the test tube as a container for our stock cultures. Like if you are able to already identify the microorganism through culture, you can make stocks of them inside the laboratory or inside the section by placing them inside the test tube. Our test tube is also known as sample tube because it's used as a container for mixing the specimen of our patient and the reagent that is used to determine a certain analyte in the sample. So that is your test tube. We also have pipettes. Pipettes are glass or plastic tubes that are usually open at both ends. This is different from our test tubes because our test tubes are open on one side and closed on the other. Pipettes are used to transfer specific amounts of liquid from one container to another and are usually used for volumes between 1 and 100 milliliters. That's actually a small amount of liquid to be transferred from one container to another. A long time ago, when automatic or automated pipettes were not yet available for use inside the laboratory, medical technologists and laboratory scientists make use of our pipettes to transfer solution from one container to another, and it takes a lot of skills to master pipetting, trying to control the amount of liquid or solution that gets inside a pipette and holding it while transferring the solution to another container. So that's one of the skills that a medical technologist should hone or develop inside the laboratory. And we are grateful today that automatic pipettes or automated pipettes are already being used inside the laboratory. So it's not that difficult to transfer the solution from one container to another. And aside from that, automatic or automated pipettes are more accurate in terms of pipetting the exact amount of volume as compared to pipettes. And I will be discussing the automated or automatic pipettes as we move on to the succeeding slides. Our pipettes can be categorized into three major classifications. So we have first is we can classify our pipettes based on the calibration marks or design. So our pipettes can be TD or to deliver or TC, which means to contain. We can also classify or categorize our pipettes based on their drainage characteristics. So our pipettes could either be blowout, which is common among to contain pipettes, or self-draining, which is common among to deliver pipettes. We can also categorize our pipettes based on the type. Our pipettes could either be a transfer pipette or the graduated or measuring pipette. So let's take a look at the different classifications of our pipettes. The first classification of our pipettes is based on the calibration marks or design seen on the body of the pipette. Our pipettes can be to deliver, or TD, which means it delivers the exact volume or amount of fluid or solution it holds into another container. This is an example of a pipette that is classified as a to deliver pipette. Based on the markings or design seen on the pipette, you can actually see here the volume, the exact volume that this pipette can hold. And then you have TD, and you have the number of seconds this certain pipette can deliver the 10 ml volume of your fluid or liquid, and the temperature. So all of the markings you can see here only means that this certain pipette can deliver 10 ml of the solution or fluid by simply draining it out for 25 seconds at 20 degrees Celsius. Okay, so when you say to deliver, you just allow the fluid or liquid to simply drain out from the pipette. Aside from the to deliver, we also classify our pipettes as to contain, or TC, which means it holds the particular volume of solution or fluid, but it does not dispense the exact volume to another container. So in order for the exact volume to be transferred or dispensed to another container, you need to blow out this pipette by using an aspirator. Our pipettes can also be classified based on their drainage characteristics. So we can classify our pipettes as blowout pipettes. This is applicable to contain pipettes. So blowout pipettes have continuous frosted rings or colored rings on top of the pipette, and they only deliver the exact volume when the last drop of the solution or liquid is blown out using an aspirator or pipetter. So these are examples of pipettes with colored rings or frosted rings that are seen on top of the pipette. Okay, so these colored rings will tell you that this type of pipette is a blowout pipette. So you need to use an aspirator to blow or drain the last drop of liquid or solution in the pipette. So another drainage characteristic of our pipette is our pipettes are self-draining, or to deliver pipettes. So these types of pipettes, you don't need to do anything to deliver the exact amount of liquid or solution inside a pipette. They drain by gravity. So in order for us to identify or differentiate between a blowout and self-draining pipette, all you have to do is look at the presence of etched rings or frosted rings on top of the pipette. For self-draining pipettes, they don't have any etched ring or frosted ring on the pipette. Okay, so if you try to look at this picture, it's plain. There are no colored rings, no frosted rings. If you compare this one to the previous picture of blowout pipettes, they have colored or etched rings. So that will tell you that this pipette is a self-draining pipette. Lastly, our pipettes are classified according to type. So we can classify our pipettes as transfer pipettes. Under transfer pipette, we can further distinguish them as volumetric pipettes. So the volumetric pipette, this is used to transfer non-viscous fluid. It's self-draining, and any small amount of fluid or solution left on the tip of the pipette should not be blown out. It's used to deliver a single specific volume of liquid depending on the volume that is indicated on the pipette, and it's shaped like rolling pins with a large belly, one blunt end, which is considered the neck, and one tapering end. The tapering end of the volumetric pipette, it's where the solution or fluid gets in and goes out of the pipette. Notice also that the large belly of the volumetric pipette is located in the middle of the pipette. Another type of transfer pipette is the Oswald fallen pipette. So this one is used to transfer viscous fluid from one container to another. And this type of pipette has etched rings. Also, the bulb is closer to the delivery tip. And this is different from the volumetric pipette because the belly of the volumetric pipette is located on the middle of the pipette, whereas for the Oswald Fallin, it's near the mouth or the tip of the pipette. Oswald Fallin pipettes are blown out pipettes. That means that any minute amount of solution or liquid that is left on the tip of the pipette, you have to remove them by using an aspirator or pipetter. Then we have the Vance-like pipettes. Vance-like pipettes have valves situated in between the mouthpiece and the delivery tip. The last type of transfer pipette is the pasture pipet. Pasture pipettes are used to transfer fluid without consideration of a specific volume. Even if the pasture pipette has graduation marks or calibrations, if you try to take a closer look at it, we don't pay much attention to the calibrations or graduation marks because the sole purpose of using the pasture pipette is just to transfer the solution or sample from one container to another. Take for example in the clinical microscopy section when we try to analyze urine samples, before we look at them under the microscope, we have to centrifuge the urine sample. When we centrifuge the urine sample, we don't directly place the urine cup or container inside the centrifuge. So we have to transfer the urine sample from the container to the test tube, and we use the Pasture pipette for that. So even if there are calibrations on a Pasture pipette, it doesn't really matter because we are actually after the transferring of the urine sample from the cup to the test tube. So that's the use of the Pasture pipette as a transfer pipette. So our Pasture pipettes can be made of plastic or glass. When it's made of plastic, it's disposable, which means to say that after using it for one sample, you have to discard the Pasture pipette and get a new one to transfer a new sample from the container to the test tube. Now we're done with the transfer pipettes. Let's move on to the graduated or measuring pipettes. For this one, we have two kinds. The serological pipette, which has graduations up to the tip and are considered as blowout pipettes, and the Moore pipette, which has no graduations up to the tip and it's calibrated between two marks and are considered as self-draining pipette. So if you try to differentiate between the two, it's very simple. If you try to look at the delivery tip for both of these pipettes, if the delivery tip has no 10 or it's not calibrated up to the 10th mark, it is considered a serological pipette. But if you can see the calibration of 10 ml, that is your Moore pipette. Here are some tips for you to remember to properly differentiate between your blowout and self-draining pipettes. So remember that if your pipette has a frosted band or two thin rings near the neck, your pipette is considered as a blowout pipette. And that means you have to use your aspirator or pipetter to transfer the remaining fluid on the tip of your pipette. The frosted band should not be confused with thicker colored rings or colored dots, which are manufacturer's code for the maximum volume of the pipette. Only blowout serological pipettes have frosted bands or two thin rings near the neck. So here are some photos of serological pipettes that are blowout pipettes because of the presence of two thin rings near the neck. For self-draining pipettes, all you have to do to be able to identify them is to look for two thin rings. If the pipette has no thin rings near the neck, then it's considered as a self-draining pipette. We also make use of micropipettes inside the laboratory. Micropipettes are used for quantities less than 1 ml or 1000 microliters, and they are to contain pipettes. Examples of our micropipettes are the following. You have your RBC and WBC Thoma pipettes. These types of micropipettes pipettes are used for manual cell counts in the hematology section. We also have the Sally-Hellich pipette, which is used for manual determination of hemoglobin, and the Lang-Levy pipettes. Let's take a closer look at our two Thermopipettes. So we have the RBC Thermopipette and our WBC Thermopipette. They have the same parts. You have the calibrated stem, the bulb, and the short stem. So let's see the difference between the two. There are four differences between the RBC and WBC Thermopipette. These four major differences are the bead color, the graduation marks, the size of the bulb, and the size of the lumen. For the RBC Thermopipette, it is easily identified because of the color of the bead present inside the bulb. The color of the bead is red, and it has graduation marks up to the 101 mark. It has a larger bulb but a smaller lumen. On the other hand, for the WBC Thermopipette, it has a white bead inside the bulb. The graduation marks are only up to the 11 mark. It has a smaller bulb but a larger lumen. So those are the differences between your RBC and WBC Thermopipette. Again, these micropipettes are used for manual cell counts. We also have the automatic pipettes. Our automatic pipettes are categorized into two. First, we have the handheld automatic pipettes. This one makes use of disposable tips, and the technologist performs aspiration and dispensing. If you're going to compare this one with the serological pipettes and the other volumetric pipettes we have discussed earlier, the automatic pipettes are more accurate and precise when it comes to aspirating and dispensing the liquid or solution into another container. Aside from the handheld automatic pipettes, we also have the automated ones. Under the automated pipettes, we have three different types. We start first with the air displacement pipette. This one is an illustration of an air displacement pipette with its parts, such as the piston, the shaft, the airspace. We have the disposable tip and the sample that is being aspirated. Air displacement pipettes rely on piston for suction creation to draw the sample into a disposable tip. The piston does not come in contact with the liquid. Air displacement pipettes are used because they are highly accurate for standard pipetting applications. However, temperature and atmospheric pressure, as well as the specific gravity and viscosity of the solution, can affect the performance of these air displacement pipettes. So how does the air displacement pipette work? In the aspiration of the liquid using this pipette, the piston moves to the appropriate position when the volume is set. If you're going to set the pipette at 3,000 microliters, the piston will have to move to accommodate the 3,000 microliters of sample. When the operating button is pressed to the first stop, the piston expels the same volume of air as indicated on the volume setting, and that is 3,000 microliters. After immersing the tip into the liquid or into the sample, the operating button is released, and this will signal for the pipette to aspirate the sample. This creates a partial vacuum, and the specified volume of liquid is aspirated into the tip. In dispensing the aspirated liquid, the operating button of the pipette is pressed to the first stop so that the air dispenses the liquid. However, not all of the liquid inside the disposable tip has been dispensed completely. To empty the tip completely, the operating button is pressed again to the second stop. This indicates that the remaining solution or fluid inside the disposable tip has to be blown out. The next type of automated pipette is the positive displacement pipette. This is an illustration of a positive displacement pipette, and somewhat they have similar parts with your air displacement pipette, like the shaft and the piston, and you also have the sample. However, they differ in the piston because for the positive displacement pipette, the piston is disposable. Positive displacement pipettes operate by moving the piston in the pipette tip or barrel, much like a hypodermic syringe. The piston touches the sample, and it does not require a different tip for each use. Positive displacement pipetting is based on direct contact of the piston with the liquid or the sample. The aspirated liquid amount depends on the dimension of the cylinder or capillary and the movement distance of the piston. In positive displacement pipettes, the tips contain both the cylinder or capillary and the piston. Now, how does the positive displacement pipette work? So you have there the piston inside the pipette moves down inside the tip to make direct contact with the sample. Next, the piston moves up to draw the sample into the tip. And lastly, when dispensing, the piston descends and the selected volume is dispensed. So that's the difference between your air displacement and positive displacement pipettes, because for positive displacement pipettes, the piston touches the sample or the liquid, but for the air displacement, it does not touch the sample or the liquid. Then we have the dispenser or the diluter pipette. This type of automatic pipette obtains liquid from a common reservoir and dispenses the samples or the liquid repeatedly. It combines sampling and dispensing functions. So here are some photos of a dispenser or diluter pipette. This photo is an example of an automated pipette that is electricity operated. So what the medical technologists will do is just press a few buttons for the machine to work, and then it's a complete walk away machine. You just have to set the machine to perform its task, and then you can go on and do other things inside the laboratory. And then after how many minutes, you already have the results of your test. Here are some things to remember when we perform pipetting using automatic pipettes. First, the plastic tips are made primarily of polypropylene, which is a type of plasticware. And your plastic tips are reusable. They can be autoclaved or sterilized. As the fluid is allowed to drain into the receiving vessel, the pipette should be held in a slanted position with the tip against the side of the receptacle. So we have here an illustration on how to properly position the automatic pipette with a tip. So for illustration A, during aspiration, the pipette is held in a vertical position and the tip is immersed to the proper depth. So take note that the user should avoid touching the side walls or bottom of the sample container. For illustration B, the sample is dispensed with the tip touching the receptacle wall at an angle and dragging it slightly along the wall. Also take note that, or we also have to remember that when we are using automatic pipettes with tips, we have to make sure that there are no bubbles or spaces that are present inside the tip or plastic tip. We also have to remember that imperfect wetting or the presence of discrete droplets of water indicates that the pipette is not sufficiently cleaned. So now we're finally done with the different types of pipettes. Now we move on to another laboratory glassware that is commonly encountered and used by laboratory scientists. So we have the petri dish. This one was invented by Julius Petri in 1887, which is a simple pair of nesting glass dishes, ideal for keeping specimens of growing bacteria sterile, and thus he was able to coin the term petri dish. This is how your petri dish looks like. So they come in different sizes and some of them even have compartments. Okay. Petri dishes are shallow cylindrical containers with fitted lids that are designed specifically for microbiology or cell culture use. It's typically made of borosilicate glass or clear plastics, usually polystyrene or polycarbonate, and they come in a variety of sizes. They can be disposable or reusable, with the reusable types able to withstand repeated sterilization procedures. Especially for petri dishes that are made of glass, what we do is after we culture our microorganisms, we autoclave the petri dish to kill the bacteria and then remove the agar. We clean the dish and then we place it back in the autoclave for sterilization, and then once it's done, we can reuse it, or the petri dish can be reused. So that's what we do, especially for petri dish that are made of glass. But for petri dishes that are made of plastic, after autoclaving the plasticware, after killing the microorganism, we automatically or immediately discard the plastic petri dish. But because, of course, it's already melted, so it cannot be reused, unlike the glass petri dish. Next, we have our beakers. Our beakers can also be made of glass or plastic. The glass beakers can be heated to much higher temperatures as compared to the plastic counterparts, while offering high clarity for content visibility and measuring. They have uniform side walls and bottom thicknesses with a flat bottom and a beak or small spout, which aids in easier pouring of any liquid solution contained inside the beaker. They may have graduated markings on their side that are accurate within 10%, although a graduated cylinder or volumetric flask is more recommended for precise volume measurements. Next, we have the flask. We have different types of flask. Actually, we have three common types of flask. The first one is the Erlenmeyer flask. So it's also known as the conical flask or titration flask. It is a glassware that features a flat bottom, a conical body, and a cylindrical neck. They have wide bases with sides that taper upward to a short vertical neck. The slanted sides and narrow neck of this flask allow the contents of the flask to be mixed by swirling without the risk of spillage, making them suitable for titrations. This type of flask is also suitable for boiling liquids. Another type of flask is the volumetric flask. This is how it looks like. It's also known as the measuring flask or graduated flask, and they usually appear as pear-shaped with a flat bottom, and they are made of plastic or glass. They are calibrated to contain a precise volume at a certain temperature and used for precise dilutions or preparations of standard solutions. The last type of flask is the Florence flask. So this is how it looks like. It's also known as a boiling flask, and it has a round body, a long neck, and often a flat bottom, but some Florence flasks are designed to have rounded bottoms, thus they need support in order to stand upright. They are designed for uniform heating, boiling, distillation, and ease of swirling. They are often made of borosilicate glass to resist high temperatures, and also they are designed for chemical resistance. Next, we have the stirring rod. So this is how the stirring rod looks like. It's also known as the glass rod. It's used to mix chemicals and decanting supernatants. It's usually made of solid glass, about the thickness and slightly longer than a drinking straw, with smooth, rounded ends to prevent scratching the surface of glasswares during use, which may lead to cracks if the glassware is later heated. It's generally made of borosilicate glass or polypropylene plastic. Another laboratory glassware is the graduated cylinder. So this is the graduated cylinder. It's also known as measuring cylinder or mixing cylinder, and it measures the volume of a liquid. It has a narrow cylindrical shape with each marked line representing the amount of liquid that has been measured. It's usually made of polypropylene for excellent chemical resistance or polymethylpentene for transparency, making them lighter and less fragile than glass. Traditional graduated cylinder is usually narrow and tall to increase the accuracy and precision of volume measurement. Graduated cylinders are considered more accurate and precise for measuring purposes than flasks and beakers, but should not be used for volumetric analysis. It has a plastic or glass base and a spout for easy pouring of the measured liquid. Plastic graduated cylinders are impact resistant, while glass graduated cylinders are chemically inert. Remember, chemically inert, they don't react with regards to being subjected to any chemical reactions. We also have vials. So these are the different types and kinds of vials that come in different shapes and sizes. They are used for general collection, storage, and transport of samples. They may be sterile, non-sterile, and or autoclavable or can be sterilized. For carrying and cleaning of glasswares, we have to remember the following tips. First, all glasswares must be washed with authorized detergent and rinsed thoroughly with tap water. Depending on the kind of glassware, distilled water is used for final rinsing. Disposable labware should not be washed, but disposed properly in specific receptacles. As much as possible, never reuse. Always wear proper PPE when cleaning glasswares. After washing, place glasswares in inverted position to allow drying. Chipped, cracked, or broken glassware should not be used. And reusable glasswares used for body fluid should be disinfected before washing. Soak them in 10% hypochlorite for 30 minutes. That's it for our discussion on the different laboratory glasswares. I hope you have learned a lot from our discussion. Thank you so much for listening and have a good day.